physically mapping the universe and its history, because as you look out to different distances, you look back to different epochs. But I figure in the 20-something minutes that I have left here, that I only have time to map towards the beginning of the universe, and then we'll run out of time. So we have this model of the universe, in which, in the very early phases, we think everything that's in the observable universe, so this is a slice through the observable sphere of the universe at the present epoch. As you go back in time, this is the envelope. There's an accelerating period, a decelerating period, and then very early on, an accelerating period. But everything that's now in the essentially radius, 14 billion light years, was one time in a region that was so small that quantum mechanics is very important. And the quantum mechanical fluctuations there end up producing scalar fluctuations, the energy density fluctuations, as well as metric perturbations. So there should be relics left, which are the perturbations, which we think become galaxies, but also perturbations that are left, which some of them should be gravity waves in the later universe. But the two scales are not the same, because of one of them, it has to do with equations of state, and there's an enhancement by equations of states. And so we know what level the fluctuations are, the energy density fluctuations are. We don't know what level the gravity wave fluctuations are. You can do speculations, so forth on that. So the basic idea is that as you look back in time, you're measuring spheres around you, and you can, in principle, measure the nearby galaxies, the further away galaxies, the first generation of stars and galaxies, and you can go back to the very beginning when the universe is 1,000 times smaller and 1,000 times hotter, and then it becomes ionized, and that's as far back as you can look with visible light. But I will show you we have a trick to look further back than that, and that's what I decided I would cover in this. So we have a little history going on, which I've marked with big events. So the very first thing was driven by a satellite, the Telstar satellite, which was an experiment by Bell Labs to see if you could send radio signals to the sky, up into space and back to the ground, so that they could do communication links. And then they hired Penzias and Wilson to see how bright the sky was, because signal noise was the issue about economics. And Penzias and Wilson used this ground receiver, which was built for the Telstar satellite, which was transmitting at a 7-centimeter wavelength, mapped the brightness of the sky at 7 centimeters. And if they mapped the whole sky, they would have made a map that looked like this. It's very, very uniform, except for strong signal from our galaxy, which is from synchrotron electrons in the galaxy, and from very hot stars, ionized energy. So that was in 1965. They published the discovery. In 1992, we published the discovery that when you looked at this with much higher resolution, so this is roughly 10% resolution, this is down to the part of 10 to the minus 5, so 10 to the minus 5 level. You see these fluctuations, cold spots together, warm spots together, cold spots together, cold spots together, warm spots together. And then the saturated galaxy across. So this is the biting coordinates. This is the center of the galaxy, and this is the plane of the galaxy, and it's saturated. And so there was the discovery, and there was a long prediction of, well, is this the relic radiation or not, which we showed it was. And then was, what did the early universe look like? And the early universe looks incredibly smooth, except for these very tiny variations, which are, we know now, primarily energy density variations in the early universe. Whatever was driving the expansion of the universe in the early days, it's probably energy density fluctuation. And that's at a level of 10 minus 5. In 2003, WMAP published this map. WMAP was basically the same design as COBE, but had radio dishes, and therefore got better angular resolution, so you can now see the galaxy a little more resolved, and you can see many more points, but you see the cool regions, and the cool regions, everything matches. It's just you see much more detail. And this much more detail is telling us a lot more about what's going on in the early universe, what the initial conditions were, and what the contents of the universe were. And I'll give you a little explanation of that. That's what I have time for. And then in May of last year, a year ago, we launched the Planck satellite, and I'll show you sort of a preliminary map, but I'm not allowed to show you. There's only a few people who are allowed to show certain things, but basically the data is being held until the calibration is done, and all collaboration members agree, which is going to be the big handicap. So here's actual data. So this is the actual data of the universe and the same sort of scale that you would look at with now at this sky looks like if you had eyes that could see 6 millimeters. It's extraordinarily uniform. There is a galaxy in here, but you don't see it because the galaxy is more than 1,000 times weaker than the universe. And there are fluctuations, but they're 100,000 times weaker. The peaks are 10,000 times weaker. So it's extraordinarily uniform. And you can compare that to, there's a picture of the sun. If the sun's not cut off, this slide cuts it off. This is a picture of the sun, and with the same kind of resolution. And if you look carefully, you can see it's all speckled, even at this resolution. The sun is somewhat speckled, and that's because there's all kinds of things going on the surface of the sun. And occasionally there are storms, like this. This happens to be the quiet sun, but there's a little bit of a sunspot stuff going on here. And if you measured this very carefully, you would find that the sun is almost a perfect sphere, but it's slightly oblate because it's rotating. And there's a difference between the universe and the sun, is the universe isn't oblate. Right? It's a much higher position than the sun. And that feeds out on the next things, the things I'm going to show you after the next 2 slides. If you zoom in, right, now the software lets us look at a sphere from the outside, but not from the inside in terms of projection. But you have to think you're inside of the sphere and you're looking out, and you see the cold regions that come together and the warm regions that come together. And that's a mark that you could set. If you imagine you had Lisa or some other object and you're mapping the sky, and you see this kind of a pattern, what that's telling you is there are long wavelength fluctuations with short wavelength fluctuations put on top of it. And in fact, when you do the analysis, there's fluctuations on every wavelength scale. But you can see that, and if you're good with your eyes, you'll actually see there's a certain scale picked out in here. But that, in the early days, that wasn't so obvious because we didn't have enough resolution with COVID. You could just see there were fluctuations on every scale roughly equal. Here you can see there's a certain scale size picked out. Right. So, but these fluctuations are the sort of the contrast scale here is about a part in 100,000. So it's extraordinarily uniform. Is the first thing. The second order, there are these small perturbations, but the universe is extremely uniform at the beginning. It's extremely non-uniform now. So there's this period where we undergo growth by gravitational instability. There's gravity pulling on these small variations to eventually make the galaxies and the voids and so forth, and eventually become nonlinear. But one of the things I'll show you is this, by looking at this map and analyzing it, you can see the processes that shape space and time are extremely linear. And if we have time, I'll get to that. Here's a picture of the sun, and it's very different. Right? It's sort of the same resolution of the sun. And you see, well, first of all, if we were able to get more resolution and look at it from the edge, we would see there's a little haze at the surface of the last scattering in the universe. But in the sun, it's very obvious, and there are much greater prominences that would stick out. But you also see there are patterns here, and you see how different the structures look here and here. It means there's nonlinear effects going on here, and that's creating sharp edges that extend over reasonable areas. I'll show you a picture of the Earth. You'll see what's formed the surface of the Earth is very nonlinear. What forms the surface of last scattering or all of space-time, it's an extremely linear process. It's at least linear to a part in 10 to the 4th. And so that means we have to get down 10 to the -9 to see that. But this is what you see. You also sort of see what looks like storm, sort of the same weather patterns we see like on the Earth. Okay, so there's a whole field called helio-seismology where you take back to this one, you take the observation of the sun. There was a telescope at the South Pole that could watch the sun for a long time. But now there are satellites, and they can watch the sun for days on end and just map the surface of the sun. And you watch these specules, and they change with time. They vary slowly with time, or relatively slowly with time. Right? And so you can break that up into circular harmonics because those are the natural modes of oscillation for the sun. And you see a speckle pattern like that for the L equals 100, M equals 90. And you'll see the amplitude doesn't stay constant. There's energy shifting from one L mode to another L mode. The L modes are slightly coupled. But you can then, as a function of L and a function of frequency, which is millihertz, you can plot out the families of the speckle patterns that you see. Right? What the frequencies are versus the L number and N number. And you see there's a kind of a shape like this. I can show you one that goes out even further out to 1200. Right? You can see these lines. And here you see some stuff more comets at the sun. But essentially there's the families of lines is rotating, the speed of sound going around the sun and direction of rotation and the speed of sound against the rotation are different, and likewise going north to south. And so you find this twist to it. The universe isn't rotating, at least not rotating in a significant amount. So we don't have to worry about the M values. We can average over the M values and just look at the typical L values. So when we calculate the ALMs, we're just going to average over the M's and find out what the A squareds are. And so when you do that, you find this is what we were seeing. I think this is around 2005. You see the power spectrum, and you see this one particular scale size, which is just below 1 degree on the map, which I was trying to point out to you. You could see there was one size where the spots were bigger and more common than others. And then there are harmonics of that at a half and a third and so forth, all the way out. And you see the blue dots are the dots from the WMAP satellite through your data, which gets out to about here. And then from MACBAR experiment, you get all these data points out here. And Boomerang sort of covers the area right in between. And since then, we've made improved observations. Earlier this year, the WMAP 7 years of observations were published. And so these error bars, you can see, and it's definitely better out to about here. And then we barely resolve the third peak, but that turns out to be important in terms of understanding how much matter versus dark matter. I'll show you in a second. And you can see the ACBAR got slightly better data, and there's a new experiment, Quad, which those of you know that Stokes parameters Q and U are, it's a polarization experiment as well as an anisotropy experiment. Because one of the things that I started people on many years ago was measuring the polarization with a cosmic microwave background to look for evidence of gravity, primordial gravity. There are a series of experiments to do that. So far, no one has seen evidence for it, and the limits are getting down, where it's interesting, but it's, we'll see. So we have now beginning to do spectral analysis, and the spectral analysis, I'll come back to in a short time, allows us to actually understand what the early universe is made out of. Just like spectral analysis of hearing a bell ring will tell you, if you have two bells that look identical, and you hear them both ring, and one's made of steel and one's made of brass, you can tell the difference. It's by just looking at the frequencies and the ratios. Okay, so now I'm going to show you what happens when you put a single lump in the universe and let time go on. Okay, so it's a little strange. Let me go back. So here's a lump, and it's spherical, but we're taking a slice through it. And you see there's a spherical shell that goes out, but the central lump stays pretty much the same. How is that possible? How does some of the matter know to stay fixed and some of the matter know to expand spherically? Well, the answer is easier when you go to one dimension, right? So you have to visualize this in 3 dimension. And so here's a 2-dimensional cross-section. You're looking at the cross-section, and you see a spherical wave go out. It actually stays pretty uniform density, but the outside's where the most mass is. But there's a central peak left, and this is just simply putting in a Gaussian distribution. Okay, so we have a simple model. The universe is made of 5 components. So one of them I will show you. We assume the universe is made of dark matter. It's made of baryons, the gas. It's made of photons. It's made of neutrinos, and it's made of gravity waves, right? And if you put a lump of energy in the universe, if you do it at a high enough energy and density, a high enough temperature and density, thermodynamics guarantees you'll get equal ratios of all this stuff. Every single mode will be occupied. Right? It's just the equipartition theorem. It says I try to put in all dark matter. Some of the dark matter will annihilate and turn into baryons and into radiation and so forth. So you'll get an adiabatic fluctuation unless you do something special. It will automatically turn out that way. So what's going to happen? So we put them here in a Gaussian shape, right? And they're in different colors. And you can guess what's going to happen. The dark matter is going to stay behind because there's a baryon-photon fluid that as the photons interact with the electrons, which drag the protons along with them, that the photon pressure is going to blow it out. So let me try and make this go forward, like collapsing things. So you see what's going on. Okay, so the photons and the baryons stay tightly coupled. The dark matter stays pretty much peaked up, but there's a little bit of Maxwell-Boltzmann tail, so it actually spreads out too. And the neutrinos interact enough that they sort of spread out. The gravity waves just go out at the speed of light. Right? They don't interact enough to be caught in the perturbation. So that's why they're not shown here. They're just a marker that shows you how far light is. So let me keep it going a little bit further. Because the magic thing happens at about 400,000 years, 0.4 million years. You see the photons and the baryons decouple. And this little bump out here, whose co-moving volume in the present epoch is 150 megaparsecs, roughly 500 million light years in radius. That the radiation comes from and gives us that image, which is that roughly 1 degree scale size factor on the map. And the dark matter is here, and the baryons are here, and you can see the baryons are being pulled by the dark matter potential wells up that way. And so let's keep going. You'll see this little residual left behind. So pretty soon the dark matter and the baryons have almost the same shape. But there's a little bump left here where the baryons are out here at about 150 megaparsecs, and they pull some dark matter in with them. And what it says, if I have a huge cluster of galaxies here, I will have a spherical shell of galaxies around it at about 150 megaparsecs. Just the residual of this acoustic wave. Finish this up. So you can look for it. So in the cosmic wave background, it makes this high peak and then the harmonics, because if you put in a narrow shape and you do this Fourier transform on it, you'll get the harmonics and so forth. So there's the fundamental in the harmonics. But if you look at the galaxy-galaxy correlation function, you see this peak. So this was in 2005. There have been 3 different measurements that were made in 2005, 2006. Now there's a whole series of experiments which are called baryon acoustic oscillation experiments. So there's BOSS, Big BOSS, and the Sloan deep survey and so forth. So this is a new ruler, right? So you have those standard candles or standard rulers in order to measure the size of the universe and so on. So there is evidence that this is truly an acoustic wave, and that it's the baryons being driven out, and as a result there are extra galaxies. And when you put the numbers in, it should be at the fraction of the scale of 4% extra galaxies outside of a big cluster of galaxies. So you have to do surveys of very large volumes. Here you see the typical size spot here, which is sort of 1 degree apart. When you look in a galaxy map at a redshift of 0.3, you're looking at a very huge section of the sky. So you have to do very large surveys in order to see these kind of objects. That's why the very oscillations sky surveys have to look for many tens of millions of galaxies and these kinds of things. But already there are data from that when you do the fits, and I'll explain about it, where the CMB, if you compare omega matter versus omega lambda for the dark energy segment, you see there's a place where the CMB is telling you it's like this, and the supernova are telling you the universe is accelerating. The baryon acoustic oscillations are telling you it's in this sort of shape. And you can put clusters in and they give you an additional thing in terms of how much matter there is. And you can also look for the amount of matter versus how the equation of state in the dark energy might change. So we're just in the early phases of beginning to add baryon acoustic oscillations to these kind of observations. Whereas the CMB and the supernova are fairly mature, and the programs are ongoing. So how do we make these kind of predictions of what's going on? So we have the sound horizon. This acoustic oscillation is well defined. You know the speed at which the sound is spreading out, right, for this acoustic wave. It's very easy to calculate. It's dominated in the early days by radiation. So the speed of sound is equal to the speed of the particle. It's the mean speed of the particle divided by the square root of the number of dimensions. So it's c over root 3. You can do the calculation. You can also calculate when the reionization, when the thing deionize, and therefore it becomes transparent. So it's a very easy calculation, and there's only a small effect, right? Because now we're down to the 1% level. To 10%, that's correct. To get it better than 10%, you have to account for the baryon living at the end, because the radiation is getting a little less important right towards the end. So you can calculate this size. You have a standard size, and now you can say how big should that be, because you know how far away it is and how big it is. Right? As you Euclidean geometry, you have side, 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 you know all the angles of the triangle, you know everything. But if you have a curved space-time, right, it can be positively curved, in which case it's like you're on a sphere, lights coming, two parallel lights coming from the equator will end up converging at the pole. There's a positive convergence. So light converges, and when you extrapolate back using Euclidean geometry, things appear bigger. Right? When you make your map using Euclidean geometry, the spots appear bigger. If it's in perfectly flat space, the spots appear just the way you calculate them. And if the universe is in fact open, then things are diverging as they go away. The lines are getting apart as they go away. So that when you look and extrapolate back, you make them look smaller. So by just looking at the scale size of the spots, right, it's all movement, the amplitude, but most of the scale size of the spots, you can tell what's the geometry of the universe. And so you look here and you see what it is, and of course it's right close to what is flat. This is within 1% of the critical density for flat using these things. So you can look at the curvature, you can look at the effect of dark energy, you can look at what happens when you add baryons. If you increase the number of baryons, this peak goes up, this peak goes down, this peak goes up. So that's the reason, you will see the reason to measure the third peak, first, second, and third peak is important. If it's made of ordinary matter, then the first and the third peak should go up and the second peak should go down. But if it's made of dark matter, the first peak goes up, the second peak goes up, and the third peak does. Because one of them is damping, one of them is the damping, and one of them is so by measuring the first three peaks very precisely, you can separate out how much is ordinary matter, and the answer is it's 4.4%, same as Big Bang nucleus suspicion, right? And this is atomic physics instead of nuclear physics. And how much is dark matter, and the answer is, well, it's about 23%. So here's where we were in I'll have to fix this. The numbers, the background is not right. I wasn't trying to hide the numbers from you. I'm trying to. Maybe I can show some of them to you. I changed the background color of these slides. There's some more that I'll say. So you can see we're improving to quite small levels. The best fit for the expansion rate of the universe is getting down to where it's around 2% error. The density parameter is hovering around what Einstein would call a flat universe, and maybe equals 1 critical density, right? So we're very close to the critical density. It's equivalent to that. The total amount in matter is roughly 27%, and 4.56% is ordinary matter, and that means what's left in dark energy is around 73%. So just by measuring these peaks very precisely and very carefully, we're able to measure these numbers quite precisely in the framework of the cosmological model we have, but we also have tests to see whether that model is correct by looking, for example, for the baryonic acoustic oscillation peak and see does it have all the right shape and the right size. And so you even know the size of the universe is expanded from the last scattering surface without leaving 9 plus or minus 1. So those are the numbers that we kind of know, and then as we get more observations and more cross-checks, we're able to tie down that the science, the physics, the formulas we're using, and the models we're using for what the components are. Okay, so we have these satellites. And so this is the other picture I wanted to show you. Here is the COBE DMR 4-year map with the best estimate of the galaxy removed. And if COBE had flipped over and measured the Earth, it would have measured this. And they looked different to me, but not enough to make a big deal out of it. Now, here is the W map. I think this is 5-year data. And here is a map of the Earth that had flipped over and had the kind of resolution that Planck will have. And you see the huge difference, right? You see these large-scale sharp features. Right? It's obvious if you had this map in 1800, you would be a great geographer and a great geologist, because you can see these various effects. Clearly, these things were together, but it's clear there's nonlinear forces working on it. Whereas you look here, there's no evidence for nonlinear forces in the universe. And we've been doing a whole lot of experiments. So there's 2 cities that are built for CMB observations. One is at the South Pole. This is the South Pole telescope. Akbar was there, now it's been replaced by BICEP. Daisy, which made the first polar visions, got replaced by Quad, which is now being replaced by SPUD. And then Atacama is 5,000 meters near Sierra Toko. Oops. Sorry about that. There'll be no movie. It's a lovely place. There are no insects. There are no trees. There are no grass. There's nothing. It's 5,000 meters. It's extremely dry, and there's some poisonous and heavy metals. So there's just nothing there. And you can see the ACT telescope being built there in this little place. But there is, in fact, 5 different experiments built around this in this area to make the measurements. And what are they doing? Well, COBE, we made this coarse map in '92. WMAP, we made a much better map. With Planck, we'll have a map that looks like this. And with the Atacama Cosmology Telescope and the South Pole Telescope, we'll have maps of part of the sky with very great resolution. And occasionally you'll see in here these little white spots. Those are clusters of galaxies that add signal to the cosmology. So we're getting a sharper and sharper image of that very earliest phase. There's a whole lot of other stuff. I would show you this movie of, well, out of time. Here is the Planck first-year map. But this includes all frequencies, so you're dominated by the signal from the galaxy. These fluctuations out here are causing microwave background. But this is the signal from the galaxy. And you can see, because we go to the long wavelengths, you can see the dust that's in our local neighborhood, circling around us, the supernova remnant, and so forth. So these are all well-known objects that astrophysics into. But if you look at it more carefully, if you go to a place where it's low dust, you actually see the fluctuations. You see the galaxy, depending on what color scale. So you see the star-forming regions and the various other dust regions. So the Planck data analysis is going along well. There's still a lot of calibration, a lot of other stuff to do, and careful modeling of the galaxy has to subtract it, because we're trying to get another order of magnitude more improved results over what we have from government. So anyway, I think I stopped at this point, because the next thing I would have talked about is survey, how galaxy surveys are done.
Time for questions and comments.
When you're removing the foreground at the high angular resolution, how do you go about that? Is it?
There are several different techniques for removing that. So the most critical thing, the most critical thing is that the CMB follows a black-body curve, and the anisotropes follow the derivative of a black-body curve. This is actually chunking the radiation side. So it's D black-body curve. It's DU or whatever. It's just a shift from that or DP. And so it looks pretty much like a black-body curve. So if you measure at many different wavelengths or many different frequencies, you can predict what the spectrum should look like. If you look at synchrotron radiation, it's very strong at long wavelengths, and it falls down typically as the frequency to the 2.7 to the minus 2.7 to the minus 3, depending on where you are. It rolls over because the electron spectrum, the high-energy electron spectrum, they are losing energy. Electrons are losing energy at a rate which is proportional to their energy or their energy squared within the other process. So the spectrum rolls over. So there's a rolling over. So you can see the synchrotron that way. Free is collisions of free electrons and nuclei and so forth. And that also has about a minus 2 on the power of frequency. The dust, you would think it'd just be thermal, it just depends on how much temperature the dust is. But the dust grains are so small that they're not effective antennas for millimeter waves. The dust sizes are microns. So you actually have a rising spectrum for the dust in the millimeter and submillimeter region. So because the microwave background is roughly flat in terms of temperature, the dust is rising as you go up in frequency, and the synchrotron and free are going down. So you need to do that kind of a fit. It's a little more complicated in terms of that the temperature fluctuations can be plus or minus, whereas the foregrounds are always positive. So you can put in some additional information. So there are various techniques. One where you just model, you fit to the frequency dependence, and you model everything. method. I find it more difficult to estimate error that way. So people use maximum entropy to try and do the best fit. So different techniques. So we want all those to agree, and for Kobe, it was not such an important thing because we were basically in the discovery mode for WMAP for at least half the sky. I mean, basically you just did cuts and you cut away about 25% of the sky, and it gets you down and then you do a little subtraction for some of the rest. They're big regions. But with Planck, that's why we're showing you the really short one. You can see there's a little bit of dusting up, and we're trying to get an order of magnitude improvement over there. And so you're beginning to have to worry about almost every part of the sky, but at a low level for most of the sky. And you're still going to have to cut out the galactic plane. Whereas you saw, we can actually make fits to those maps and subtract away models, and so on the surface they look good. And that tells you, fortunately, we live in an epoch in the temperature of the radiation is such that it's thousands of times brighter than the galaxy.
Any other questions or comments?